Hello everybody, welcome to this tutorial on disk scheduling algorithms. This tutorial is prepared for those who need an assistance in disk scheduling algorithms. So we have basically a few types of disk scheduling algorithms. The first one is FCFS, which is first come first served, and the second one is SSTF, the shortest seek time first. And we have the elevator scan algorithm, and we have circular scan or C-scan algorithm. Also, in addition for that, we have the look and the C-look. So in this tutorial, we're gonna cover these algorithms one by one. So let's get started with the first one, with the first come first served, FCFS. So given the following queue, we have 95, 180, and 100, 119, and 11, 1, 2, 3, and so forth. So let me just try to pick an annotation here, cursor, show cursor, okay. We can choose a, okay, this is highlight clicks, right? Okay. So let's start with the first one. We have this following queue, okay, and the question said that with read write hit initially at track 50. So initially we are here at track number 50, and the tail track being at 199. Let us now discuss the different algorithms with the first one first, or first come first serve. We start with 50. Okay, when we started with 50, we got 95, so we move to 95. We are here. After that, we got 180, so we move to 180. We got after that 34, we move back to 34. 119, we move to 119. We move to 11, we go back all the way to 11. Move a little bit forward to 123, so we are here. And last thing we go 62, and finally we get 64. So notice here the first come first serve, we just take the first and we just move across all the entire values from the left to the right and from the right to the left according to the given value. So all incoming requests are placed at the end of the queue. Whatever number that is the next in the queue will be the next number served. So using this algorithm does not provide the best results. And in order to determine the number of head movement, you would simply find the number of tracks it took to move from one request to the next. For this case, we move from 50 to 95 to 80 and so on. So from 50 to 95, we have 45 tracks. If you tally up the total number of tracks, you will find that how many tracks it had to go through before finishing the entire request. So in this example, we had a total number of movement of 140 track. So the disadvantage of this algorithm is noted by the oscillation from 50 to track 80 and then back to 11 to 28, 123, then to 64. So as you will see soon, this is the worst algorithm that you're gonna ever see in the scheduling algorithms that we want to talk about here. So you can count the number of tracks, movement for the tracks. So we got a 640. So from here you can see the number here, here, here. So if you sum up all these tracks, you're gonna have 640. So let's now move on to other algorithm, which is known as the shortest seek time first. So which is known as SSTF, shortest seek time first. In this case, we started from 50. We have this queue. Let me just bring the queue, the numbers. So we started all the time. We started from 50, and so here, let me just put this. Okay, we can. What is sticky note? Okay, new sticky note. Okay, okay. Let me close this. Okay. So we got, from here we got 95, 180, 34, 119, 11, 123, and 62, and 64. In the shortest seek time first, SSTF, we just look for the shortest and the closest one to us. So here we begin with 50, right? So we seek the queue. What is the shortest one that closest to us? From 50 we have 11 here, we have 62, 64. So the shortest, or the nearest one, the closest, is the 62. So we move from 50 to 62. So we look after that. We just make other look to the queue, and the shortest one is 64. So we'll move to 64. Next, we need to decide what is the next step. We have 34, 11, so it's obvious that 34 is the nearest. We are on 34. We look for the shortest one, so we can see that it's 11. We are in 11 now. We need to look for the nearest one. So if we have 95 and 180 and 119, so the nearest one is 95. From 95 we move to the nearest point, which is 123. 123 will move on to 180 and so forth. So this is the shortest seek time first algorithm. In this case, the request is served according to the next shortest distance. So starting from 50, the next shortest distance would be 62 instead of 34. Since it's only 12 tracks away from 62 and 16 tracks away from 34, so we take the shortest. So the process would continue until all the processes are taken care of. For example, the next case would be move from, we consider all these cases and step by step. All of this seems to be better, service being that moved at all a total of 236 tracks. This is not an optimal solution. So there's a great chance that the starvation will take place. The reason for this, if there were a lot of requests close to each other, the total request will never be handled, since the distance will always be greater. So you should notice this case. Okay, you should notice this case, that there is a chance for starvation, because if there were a lot of requests close to each other, for example, we have a 95, 96, 97. We have many requests are close to each other. We can have some kind of starvation. Okay, because the other request will never be handled, since the distance will always be greater. So you should take care of this. A chance for starvation in the shortest seek time first. Let's move on to the elevator algorithm. Okay, when we talk about elevator, it's just like the real elevator. You just have one way. You go to the top of the maximum. You start from 0, and you have, for example, you have a building, right? You have 10 floors. So when you click on the elevator button, you need to go to the 6th floor. So you click the button, you go to the 6th floor, and if there any floor after 6, you're gonna reach it. Okay, but it's one way, either from bottom to the top or from top to the bottom. So just keep this cycle, bottom, top, top, bottom, and so forth. So the elevator algorithm works like the real elevator in the real life. It scans down towards the nearest end, and then when it hits the bottom, it scans up, servicing the request that it didn't get going down. If a request comes, or if a request comes in after it has been scanned, it will not be served until the process comes back down or moves back up. So this process moved total of 230 tracks. So if you count the number of tracks from here to here to here to there and so forth, you're gonna have a total number of 230. In the previous example, we had 236. So this is much better than the shortest seek time first. So let's try to track the algorithm here. Okay, we start all the time from 50, and we go down to, like the real elevator. So from 50, we go to the nearest one, which is 34, back to the nearest one, 11. Okay, and then we go to 0, because we have the first one is 0 all the time. We go to the first one, 0. Then we move from 0 to the nearest one, which is 62, and then we 64. From 64 we move to 95. From 95 we move to 119, and from 119 we move to 123, and finally we move to 180, and this is the maximum. We stop 180, and if we got something less than 180, we just move back across all the way to 0. So all the time we need to reset to 0, and we go to the max. So max here is 180. So this is known as the elevator scan algorithm. Okay, we see this the approach of elevator. We got 230 track and 1 tracks. Once again, this is more optimal than the previous algorithm, but it is not the best. So we see elevator is pretty much good. So until now we have 3 algorithms: the shortest seek time first, the first come first served, shortest seek time first, and elevator, and finally, or the not finally, the circular scan or C-scan. Okay, in C-scan they use different approach. C-scan is known as the circular. I have a difficulty in pronouncing this. Circular. Okay, circular scan. Circular scan works just like the elevator to some extent. So it's pretty much like the elevator, but it begins its scan toward the nearest end. So we begin the scanning toward the nearest end and works it away all the way to the end of the system. So it works like elevator. We begin from we begin from 50. We move all the way to the start. Okay, toward the nearest end. Then we move all the way to the end, and then we just back to, as you can see here, to 62. So once it hits the bottom or the top, it jumps to the other end and moves in the same direction. But keep in mind that the huge jump does not count as a head movement. So this huge jump from 0 to 199 from this end to this end, we don't count it as a head movement. So the total number of heads movement for this algorithm is 187 track, but it's still, this is not the most efficient or sufficient. So let's try to trace the algorithm here. We started from, let me just get the input. We started from 50, right, from the beginning. We moved to the, you can decide to this side or this side. So this we move to the left. So like the elevator. So here we have 50. After 50 we got 34. 34 got 11 from here. And we move after that to the end, which is 0, right? Next we move all the way to 199. But this, we didn't consider this as a head movement. So we are in 199. We move to the next nearest jump, to the next nearest point here, which is 180. From 180 we move to 119 and 123, 123, 119, and after that 95, 64, 62, we stop here. So this is the circular scan or C-scan. Okay, this algorithm is much better than the elevator because we have 187 tracks here, and this is pretty much better. But this is not the best. Now we want to take a look at the last one here, which is the C-lock. The C-lock algorithm. In C-lock algorithm, we have an enhanced circular scan or enhanced version of circular scan. In this scanning algorithm, the scanning does not go best to the last request in the direction that it is moving. It is, for example, here in the previous example, we moved from 50 to the last point here, 0. In this C-lock, okay, enhanced version of C-lock, of C-scan, we have the C-lock. And in C-lock we have different approach that we move from not to the last end but to the last point, the not the start, I mean. So the start is 0, but here we move to 11. So this is the main difference. Okay, but not all the way to the end, as I said, just to the furthest or the latest request available in the queue. C-scan had a total number of 187, but C-lock reduced to 157. So from the both sides, from the left and from the right. So instead of going to 199 to the last point that we move just to the last point in the queue. So instead of going to 199, we have 180, and we have 180, right? So we have 19 from this side, and we have we have 11 from this side, so we got about 30. So if we subtract 30 minus 178, we're gonna have 157 track. So this is much better than the previous one, the C-lock, the C-scan, I'm sorry. So C-lock is the best. So as you can see here, we started from the first come first serve FCFS, which has about 640 tracks. We move forward to the shortest seek time first, the SSTF. So we got an optimized version with about 263 tracks. a little bit forward with elevator, we got 230. And circular scan, we got 100. Circular scan, we got 187. And the last thing we got the CLOOK algorithm, which we got 157. So we can compare between them and see what is the best. So from this, you were able to see that a scan change from 644 total hit movements to just 157. So you should know now that we had an understanding why the operating system truly relies the type of algorithm, in the process on the the requirement in the required requirements, right? So when it's dealing with multiple processes. So final note here, it is important that you draw out the sequence when you're handling algorithms like this one, because you have a visual representation, you can see everything and how it's going. So one would have a hard time trying to determine which algorithm is the best by just reading the definition. So with visual representation, there is a good chance that without the drawing, you gotta have a lot of miscalculations. So every time you try to redraw everything and see it visually with your eyes, and just count the number of tracks. So from here we can say, okay, 50 to 34 we have 16, we have 34 to 11. So we got 23. So 23 and 16, we got 39, and you just sum up these. We got 2 plus 31, we got 33, and you sum up from 95 to 119, you got about 24, and here we got 4, so 28, and you just sum up all the stuff here, you got 157. So this is how you calculate the total number of tracks between in the movement for the hit. So this is pretty much the disk scheduling algorithms. I hope you benefit from this tutorial. Don't forget to subscribe to the channel. Ahmed Nasser all the time with you. So see you in another video, another tutorial. Thank you again for watching, and see you soon.